Right now,
We'll just give it one more minute and start in a minute. Hello, everyone. Good afternoon, and welcome to this. Going to be a wonderful session. Dr. Satyanarayana doesn't require any introduction from me to this audience. I just bring some salient feature of his coordinating EdSet forums. As all of you must know, he has coordinated EdSet for almost 22 years, become a face of EdSet curriculum in TFR, and about 930 something plus EdSet collegiums, which he has coordinated, and what fascinating speakers here. And I requested him to do this specially to just give us some brief ideas about his career here in terms of his scientific contributions which he has been doing, as plus less teaching a number of students. I don't know, maybe he even must have lost count of them. So I'll request Satya now to please.
Can you hear me? Yes. Okay. Good afternoon, everyone. And before I begin, I really sincerely want to thank the asset coordinator, Parag, who had kindly invited me to give this talk. And also, I must thank Sandeep. Sandeep Trivedi is not here, I think. He was another one who was persisting that I should give a talk. Okay, thanks, Jerome. He's also just walking in. So a bit of a disclaimer is that since he mentioned that I should kind of give a overview of the journey of last about 40 plus years, so it's of course impossible to cover every aspect of what we have been doing all this time. Also, but it is also difficult for me to sort of go in any deep depth in in any of those topics. So it will be just for pleasure. I think it will be just you just keep seeing and enjoying, and there's nothing deep technical details that I'm going to kind of bore you at. Of course, you are always welcome to kind of stop me, and then we can discuss either during the talk or afterwards. But otherwise, it will be just a few photographs all through that is going on. Yeah, so just a word about the title. So it sounded a little bit technical. I think some people have asked me. So, I mean, I only say that the kind of uh, the job of an instrumentation engineer in general, at least in this campus, is trying to kind of pick up very tiny charges, which are typically the detectors produce, and then do a whole lot of things with that, depending on what are the kind of physics observable that you would like ultimately to record that, right? So different experiments have different demands, a different number of channels, and different way of putting the data in, and so on and so forth. So the journey has always been kind of adopting these things to specific physics program of the institute. So since it is all that about nostalgia, so these are two very defining telegrams that I received from TIFR. One, sometime in July, early July, this telegram says that I should appear for an interview on 14th of July, the 2nd July and 14th of July. So remember these dates, and etc. So, but it's interesting to say that I actually applied for a research scholar position in computer science group, but I was actually called for a scientific officer interview. It's very interesting. Now, a month later, you can really see the time scale. Within a month, the TIFR already offered a job. So that is a kind of speed that we had olden days when you had telegrams, and so this was sometime in August. And with a very fat salary of 700 rupees per month. So that is the scientific officer post. So they are obviously the most important telegrams in my life. It's always great pride and pleasure to talk about a work that we have been doing in KGF. And the very first opportunity came about with this very, very famous Mahabaleshwar school in high energy physics, experimental high energy physics school. It was, I think, run by Tuanwar and Prince Kumar Malhotra. So in a way, I think it was probably the best school that I attended, because the speakers were from all over the world, including Fabio Sauli and Jacob from CERN, etc., who really taught basics of detectors as well as the instrumentation, which has gone a long way in that. And I think it was a defining moment again to be able to learn from such kind of experts very early on. My first asset colloquium here in the same hall was actually sometime in 1987, I think in April. I was very fortunate. It was actually conducted by Professor S.V. Damle himself. That time again was talking about, by that time it was like 3-4 years, so we already developed the entire data acquisition system for the so-called proton decay experiments. And these were actually the transparencies that I'm actually, today you'll find quite a lot of those transparencies, which I scanned mainly because I wanted to keep that nostalgia feeling for myself. In fact, way back, even when I was in Kolar Goldfields, these were, some of you oldies will remember, this is the way you do programming those days, right? You actually write mnemonics. Let us say this one is for Zilog 80, Z80 microprocessor, and then you quickly convert them into opcodes and enter them into the microprocessor kits, and then you kind of run this code. So this was the kind of dates. Somewhere, I think it is there, 85, probably this. And even that in Kolar Goldfields, we used to organize, that time I used to call seminars, and then we had maybe about 70 or 80 colloquia. So ASSET was not the beginning that I was kind of organizing, but there was something precursor to that. So let us go a little bit in chronological order. All of us, many of us as bachelors, started our professional life in KGF. And for all of us, the gateway to major scientific experiments at KGF is the so-called Champion Reef mine. And this particular shaft is called Gifford's shaft. That is how it's named. It's one of the world's deepest shaft. It's 2 kilometers down with just one drop. You reach in about 4 minutes the 2 kilometers distance, and that is because they run very slowly. But yes, of course, all that. But if you ask them to run fast, you will reach in 3.5 minutes. But there are several experiments spanned over 40 years, 50 years, which were conducted at different levels, underground. Many of them are something to do with looking at muons, cosmic ray muon study, later on become neutrino physics studies. And then when many of us were hired, they were for proton decay experiments and so on. So this is a very iconic BGML British building in which we had the laboratory situated. It was called Cosmic Ray Laboratory. Probably you can see. You can also see some of our ex-colleagues. And it was great fun. The life in Kolar Goldfields was much different than what many of us here think about it. So this, you can see the most modern telephone instrument that using which you make calls. And this is the typical attire that you use to go underground. The one that this person is inside is what you call a shaft, and a cage we call cage, but it is like a rack of a lift. But of course, absolutely dangerous with the way it moves dangling around. Once in a while, the latches, probably if somebody forgets to latch at a proper place, you actually end up going very fast somewhere unknown territory, and then you can be quite scared of such experiences. Almost everyone in this audience would know this is the most iconic experiment that was conducted. I was barely 3 years at the time, 1965. But I want to kind of start from here to show that how a cleverly designed an experiment can actually do wonderful science, not necessarily to use the state of the art and so on and so forth. Look at this picture here. You have all these are vertical columns of that you see here. The outside, the 2 columns are plastic scintillators, which you can see here. They are actually used as a trigger. So they actually look at, let us say, the particles for which you would like to kind of freeze the data. And inside you have 3 columns of neon flash tubes, right? Neon flash tubes are very thin, about a centimeter diameter, something like fluorescent lights. And then when you trigger them by applying potential, they kind of flash as the particles passing through triggered by these scintillators here. And you also have an inch long, thick scintillator blocks to block the low energy stuff. Now you can kind of see, so this is the same picture. So these are scintillators. These are these columns of neon flash tubes, and then the thick lead sheets. And you can kind of, I'm not going into the experimental details, but the tracks which are very, very large angle, it really tells you that they are not coming from atmosphere. Okay, and you are able to kind of record them with a good precision because of the neon flash tubes here. And of course, you kind of connect them, and you see the origins mostly either on the air surrounding the detector, or at least one of them is maybe on the material around the detector and so on. And of course, you also required to record the time of the event, right? So nowadays you have GPS to a level of tens of nanoseconds and so on and so forth. By the way, I mean, the way you record the data is basically by a camera film. So to which the trigger also goes. So whenever the neon flash tubes flash, you actually the camera clicks the picture. So that is how the data is recorded. And very intelligently, you also put a wall clock on the detector, so which means it will also record the time of the event. So I considered this to be the most creative of all the experiment details. Okay, yeah. Yes, usually go by the overall azimuthal distribution, which if you look at the distribution, it will probably go around 75 degrees. So anything beyond that is not something which is generated in the atmosphere, but something which is coming at much larger angle in this kind of cases. So any such detectors, which not the one that I was kind of mentioning before, but if you want to use so-called electronic detector, right? What we want to do for the purpose of instrumenting that, you can say you would like to kind of detect the ionizing radiation, right? The radiation that ionizes inside your detector, you would like to somehow capture at the end. And always you want to detect this because there is a small signal. Usually the detectors are biased such a way that they only produce small signals. The real game is to be able to kind of build your instrumentation with a good signal to noise. So therefore, if I want to kind of capture such small signals, is always a big challenge for a instrumentation engineer who designs many times the electronics for nuclear or particle physics. So why do you process those small signals? Because you want to extract something very useful information from them, and ultimately leading to some physics measurement. So now if that is a kind of job, and usually if I want to oversimplify any detector and say what is it kind of comprised of, it is like saying that from a point of view of a current source, maybe a capacitance that represents the detector capacitance. You will find that quite a lot of detectors in some way are either a parallel plate capacitors or a cylindrical capacitors, a lot of them, not necessarily every one of them. So you could really represent that capacitance plus all the stray capacitance put together as a capacitance here. And there is also a kind of a large internal resistance that is associated with the internal detector and so on. So of course, it happens that if the detector is not producing any ionizing radiation, but still there could be a very small current. Sometimes we call that as dark current and so on. So therefore, you need to, yeah.
What are you about the wall clock? So your data rate must have been like a few per minute at most.
Yeah, you are, in fact, typically around 2 kilometers, 2.5 kilometers below the Earth. So therefore, the muon rate maybe is about a couple per day. Okay. In fact, some of our colleagues went around 2.7 kilometers below the Earth, where they found for what they call about 200 meter square days, means meter square is the area, and days, they didn't observe even a single count. So they actually told the guys in the mines that if there is an event you find, please write a postcard to Bombay, and then we'll come. And so that is the fastest data queuing system that they had those days. Yeah, so I'm sorry. That is the whole idea. In fact, that particular experiment also gave a kind of an indication that is the best location to do a neutrino experiment. So later on, subsequently, a little higher, 2.3 kilometers was where this experiment was conducted. Okay, so this experiment is actually, you can see 2.3 kilometers. This was the proton-decay experiment of 1980. This incidentally happened to be the thesis experiment of Mondel. You can really look at what I want to all you look at is late 70s and early 80s are not still the age of microprocessors or even high density electronics and so on. So people had to develop a lot of that logic, entire control system they had to develop by using discrete electronics. And you can imagine there are like something like about 1400 or 1500 tubes of proportional counters, which need to be kind of handled both in terms of triggering the data acquisition system, etc. You can really imagine how tough it is to build the electronics for it. So anyway, let us move on. So this is how the entire system used to kind of work for them. So starting all the way from the proportional counters, you had standard amplifier discriminator and put the data on a RAM. I'll come to that in a minute. And then start looking for bringing each of these data through a very, very long, very crucial chain of timing and digital. So you kind of clock each one channel, bring the data in, digitize the data, then take the next and so on, because they're only, see, the kind of occupancy levels of each of these, even though I said 1400 tubes, but the number of tubes have signals maybe barely around 20, 30, 40 of them, because the typical tracks, when they go through, you will have about 20 or 30 tubes firing them. So bring all that and do, put that in the system memory, etc. But remember, late 70s, the hard copy that you have to do is what is called paper tape puncher. So it's kind of no hard disks, no floppies and so on. So you actually have to punch the data. Maybe I'll show you in a second what it is. And that is how the data gets recorded. So when you asked like the number of events, so even if you have to really, after you do set up something, if you want to know whether the triggers are coming or not, we need to kind of sleep there for some time so that you see that, okay, there is an event recorded. That means the entire system is working. And you don't have to remember whether it is a muon or ordinary chance, because the muon will have typically around 15, 20 sets of data. So it will take longer time to punch compared to a chance, which is about 5 counters or 6 counters. So you can actually hear how many, how long the puncher is punching. Then you can say, this looks like muon, and the other one is a chance, and so on. So that is what, that is, that's fun. So this is what I was telling you. So the data that is recorded is on a paper tape puncher, which will have the 8 dots that are printed like a standard ASCII data, and then the puncher keeps moving forward. So when you bring the tape, you actually do the reverse of it. You bring the tape, put it on a on a reader, and then you analyze the data. I mean, the data is so little, but in spite of all this, looks very rudimentary way of doing things. But when you see such pictures of your entire detector, the tracks of various types that are going through, the muons, 2 of them parallel muons going to the kind of showering of events, the so-called confined events, where the events, everything is kind of happening inside. There doesn't seem to be a track coming from outside nor leaving inside. So what we call confined events or nucleon, proton decay events, and so on. All these kind of things were possible by using such rudimentary kind of electronics that were built, but very reliably. So this is the time when many of us joined for building up a much bigger and a little bit of shallower level. It is around 2 kilometers below the ground. What you see on the left side is the 6 meter long proportional counters, which you will also see here, which are about 10 centimeter by 10 centimeter cross section. They are being lowered to go to the experimental cavern, which is around 2 kilometers below. The only way that you can do is in the night time, because daytime all the miners will be going down. So therefore, you tie all these counters on the top, which is actually the rope, or you can say the chain, which is holding the cage. And then you tie it up around and then take them in bunches. And once you reach that place, again, put it in such kind of trolley and push them and so on. Obviously, it is quite a hard job. Now, yeah. Yes, there are 2 big drums, and then one is winding down, one is winding up. And each cage has just one rope connected and one chain connected to that. Yes. Oh yes, that's it. But the Bharat Gold Mines Limited, which all these people were trained by Britishers, the kind of safety record that they have, especially since they took over by BGML, is extremely really good. I never saw in in 10 years I was there was not a single accident to that. And they have a very, very strict maintenance, weekly maintenance, and they take care, they measure the rope, the elongation of the rope, and see that everything is fine. They change the entire rope. I think the rope is of this thick, probably around 3-4 inches. And then they change all 4-kilometer rope very frequently and so on. The safety record is extremely nice. Yeah. So this is the experiment that many of us were participated here. The previous experiment had about 1400 proportional counters, and this one, there are 60 layers of roughly 60 detectors on each layer. So there's about 3600 here, and you can also see that there are beta counters on 3 sides, each one of them 2 layers, and again roughly about 60 counters. So that makes another 6 layers and so on. And in the front, we also had another detector, which is for magnetic monopoles, which came up later. But so this itself is really a big scale experiment. When you think of the instrumentation, or even for that matter, making detectors, it was a big enterprise. All these detectors were sort of built and tested in Kolar Goldfields in the lab, and subsequently we went to BEL and got them built there as a production thing. So this was the lab. Okay, this is at 2 kilometers below the earth. Yeah, so it's black and white days. So all these photographs, of course, look black and white. You can actually see the counters are arranged in orthogonal fashion. So there's one layer here, and the other layer is perpendicular to this. Then that is how we can get XY coordinates as the tracks move by. And the front end is sitting right attached to the anode wires here. You can see at the center you have the anode wires, and they just connected to the front end preamplifiers here. And then right below here is to convert the analog signal into, let's say, logic signal, which we call discriminators and so on. So the detector is being installed and commissioned here. And remember again, those days there is nothing like a CAMAC or VME or whatever. Everything was kind of designed from scratch, all from basic, discrete chips. And the form factors that you have in your hand is in your hand. You don't have to follow any standard modular instrumentation. So therefore, you design the entire structure, the entire, form factors, the power supplies, the cabling, everything you choose. So that is the good part about it. You are not confined by what, particular standard says. So you can really see this was that by the time we started designing, the microprocessor came on the horizon. So therefore, all our boards were designed using 8-bit microprocessors called Zilog, Z80. Okay, so you had, let us say, the entire detector is divided into 8 segments, 16 segments, sorry. And then each one of them takes care of one segment of the detector, and all the control, data queue system, monitoring, everything is actually done by one station. So you can call this as a station. Each station has, let us say, a CPU board, and also the one that controls the other one. Again, you should remember, resources are at premium. You had a huge memory of 8 kilobytes, on which you should write all the code that can take care of that particular segment. And you run at a ultra high speed clocks of 4 megahertz. And then therefore, you should be able to finish off data acquisition with that kind of speeds before the next event happens. As Sudipta mentioned, luckily the event rate is not very high, but still by the time we came here, the number of jobs, the number of parameters that you need to acquire are quite large. And you keep doing monitoring at the back. It's not that the CPUs are idle. When you don't have events, you keep on monitoring the health of the detector. One of the best thing about these kind of so-called non-accelerator experiments is it's not that somebody is giving a clock to you to say that this is the time that you need to record the data, the way it happens in accelerators. Here you need to kind of look at generating so-called trigger by yourself. So how do you know that a particular event is of interest to you? Is by looking at the topologically the hits in the counters, and then ask a question. If it is a typical cosmic muon passing through, what kind of hits that you will see? You will of course see straight lines, for example, if there is no magnetic field and so on. So therefore you ask for a number of hits accordingly. Or what happens, like what you asked about a very large angle event. So they confine only to few layers, but each layer might have a larger number of cells hit and so on. So ask your electronics to look for such events. And the best elements by that time we started designing to look for such thing is what is called lookup tables. And lookup tables are best implemented inside EPROMs, electrically erasable programmable read-only memories. So that was a very nice idea that you put all these tables in a lookup table, and then as the events happen at live time, you actually generate the interesting events on which then you kind of compile the entire data, collect all the data. So this is the trigger system that runs through. So it's another something very interesting that I want to share here is again, those days, how do you actually record the data from as the data is streaming out from the counters? Okay. For example, what I do is I'll open all the counters to start giving the data. I don't know whether that is going to be interesting or not, but you use those as data lines into a static RAM, data lines of a static RAM, and run the clock, which will keep moving the address, moving at, let us say, 5 megahertz rate, right? So that means what I'm doing is I'm actually literally printing the status of, let us say, 8 lines, 12 lines, whatever it is. So if the data is there, it will become low. If the data is not there, it will become high and so on. At the end of the day, what you will see is a kind of imprint of the pulse that you have. Now, by the time the trigger system will be working on whether to generate interesting event or not, and when that does it, you actually freeze what you are recording it and go back and actually ask, you run through the memory and say that, okay, now tell me whether you have data. If you have data, at what time the pulse profile changed from high to low, and then you count how many clocks that I have. So I can actually see what is the width of the signal. I can also see at what stage the trigger happened. So one will give you the time delay. The other one will give you what is the width of the pulse, And I will use a formula to, basically the width is logarithmic proportional to the height of the pulse. So I know what is the height of the pulse, and I can calibrate and say this is the energy of the particle. So I have the timing and I have energy, and of course I have topological information. So I can construct an event based on that. Very beautiful concept where you don't need a high tech to be able to kind of see data coming at high speeds, able to record them, and so on and so forth. Even the data, I told you there are 16 stations in the cavern, and each one of them are synchronously picking up the data. How do you communicate with the backend? There is no Ethernet those days. There is no USB. There is no nothing. Right? You design your own. So we designed our own. We actually designed a scheme where there is a host computer and there are n number of slaves, and they will be able to talk to on a 8-bit parallel bus. And the entire protocol has been designed very beautifully. So there is no issue at all picking up this data. Of course, data speeds are 30 kilobytes per second. Okay. So not 4 giga, 5 gigabits, etc. But that is good enough for us. So this is how you develop your entire system from scratch. So whether it's from proportional counters to front end, putting all the data into analog, digital, and then pick up the trigger and get the data onto the host computer, etc. We also had that time limited data acquisition of analog information. I only told you some time back that it was only the width that you convert. And of course, depending on the lower energy scale, probably you don't have much of error. But if the numbers are, 20, 30, 40, 50 particles, then the data collection or the accuracy of calculation of number of particles won't be so good because it's a logarithmic relation. But we decided also to do a sample analog information directly so that you'll be able to kind of cross-correlate this data well. So we even implemented that later. Those days, even making a PCB of about 50 centimeter by 50 centimeters, it's a great thing, right? There's no computer. How do you make PCBs? You actually put tapes, take a table and put a light below and put a glass on top and start putting the tapes, and then take a camera and, and process it and so on. You can imagine how to build such kind of boards. So one of my first job in KGF was to kind of design a kind of circuit which will test such kind of complicated boards. Okay. So you also have to make, when you have 3,600 counters, how do you quickly install, commission, and make sure that everyone is working fine? You can't take oscilloscope, pulse generator, and so on with each there is about 6 meter height, right? You can't go up and down. So take a small kind of a board which will generate signals when you connect to the front end itself, drawing power from there, and you will be able to kind of test them very quickly and so on. All those kind of things are necessary when you want to bring up an electronics, bring up a detector in short time. Remember, it took only a couple of kind of years from scratch to build the entire thing here. So, and the back end, you will of course have a personal computer, but when I say personal computer, it is actually ZAT based dabba. Okay, and you can look at these numbers, 64K byte printer and so on, right? And columns and so on. I will come back a little later and to tell you about this bubble memory device, which we ought to use instead of using a floppy drive or some such thing, because the environment there is very dusty, and also it's very highly humid. So we used to use this device. Unfortunately, this didn't live for long before other storage devices came into being. Yeah, so nevertheless, I mean, there are lots and lots of electronics that was built from scratch, as I mentioned to you. So it was a great experience, especially for young engineers, many of us who have joined around that time. It was a fantastic challenge to build boards like this, make them work, thousands of such boards, and many of them obviously had to be made first by wiring them and testing them, etc. So you can really look at how dense these boards when you have to wire them, right? And I mentioned to you how difficult it is to run the experiments down, because you can't go underground whenever you like to go, because there is some time, and the main priority is to so-called get the gold out of it, not that you go and do proton decay experiment there. So what happens if your experiment doesn't run? There are so many ways by which the experiment can stop, and until next day you wouldn't know what's happening. So therefore, we also needed to build some kind of fault tolerance there, something like a watchdog kind of thing. You pick up all the important parameters, power supplies, computers, and what happens to, if the computer is running well, it will run in a known area of the code, right? And if it goes outside that code, that means the computer is hung up or something didn't work. So what you do is, if the code is running within known, you keep on plugging in some kind of triggers so that the monoshot keeps firing, saying that everything is fine. Now, if it goes out of the loop, the monoshot doesn't get a trigger, and after some time it gives up. And so those kind of simple things. And then there is a bulb that is sort of kept in the telephone operator's room underground, and that person will see whether the bulb is on or off, and he will call you, then you will go down and then, kind of pick up, there may be something wrong, some experiment, something failed, and then you correct it. All these are required if you want to do good, let us say, experiments with good runtime. Okay. As I mentioned to you, we also had to build another smaller detector in front of the big detector, which was mainly looking for monopole triggers. It was very similar in terms of data acquisition, except that we needed to kind of take care of slow moving particles to a level of around 10 power minus 4 C. So therefore, all those stretching of the triggers need to be, instead of few hundred nanoseconds, they had to be like few tenths of microsecond. Otherwise, the techniques were something similar. We also had to run the detectors at not using so-called P10, but maybe helium and other mixtures and so on. Okay. So I mentioned to you that the old experiment had these paper tape punchers as the device, but when these magnetic bubble memories came in the horizon, so we started actually picking up the data which is already coming and getting punched on the paper tape punchers, and we actually ended up writing an operating system for bubble memories. Bubble memories operate just like it's like the kind of a matchbox size, but with a huge memory capacity, 120 kilobytes for that matchbox size. So you write device drivers to be able to kind of operate them just like a file system that you see in a disk operating system, and able to kind of use that to store programs, data, everything. And it become much simpler because now you don't need those paper tapes, which are very clumsy to handle it. Okay, so the entire system was redesigned, and the same thing used to happen for monitoring data. The only way that the data is kind of looked at is the data is printed on a a continuous stationery. You have to look at and then find out what is the monitoring data. So then we ended up actually writing developing a crate-based system. Again, imagine there was no crates existed, no VME, no CAMAC at that time. But we designed our own crate-based system with a controller, with various executive modules run by a backend system, that for each one of the, let us say, monitoring type, we have a different event that can take place. So this happened and it really improved the data quality and so on. So, yeah.
So trigger rate is very small.
Yes. Yeah.
Counter rate.
Yes.
Could be few hundred. Right?
Correct, correct. Yeah. This monitoring is anyway is a counter-based monitoring. So you could select, I mean, you can multiplex a bunch of channels, maybe typically in a cluster, and then you count them. When it comes to the trigger, of course, the trigger rates will come down the moment you look for trigger condition, either 5 out of 11 or 4 out of 8 and so on and so forth. The rates fall off. And the actual events, as I said, it's hardly 20, 30 per day, even in the phase 2. So therefore, it becomes easier for you to collect the data. So the data sizes are not very big as such. Yes, yeah. I just wanted to say here that, you know, they were the days of where you really do something from scratch. It's not, I mean, luckily, there is no internet available. So the best part is you don't Google and just, you know, download codes. Now you go and ask somebody, they will say that, oh, Raspberry, in 10 minutes, you will make a code. How? The person will bring from Lamented Road, connect it, download that code and runs in half an hour, the LED blinking. But here it is nothing. You really, I mean, you can argue that it is very inefficient. But the point is that in those days, somebody has to write a device driver under MS-DOS to understand how to run certain utility. You can imagine, you don't even know how an operating system works. And so therefore, it is very nice that we could actually develop these things at that age, because the project has sort of gave us that opportunity. Then we moved on, of course, to D0 in Fermilab, for which we needed to build large number of scintillators. If you come to the first floor C block, you will see a sample of these detectors. These are scintillator, plastic scintillator, with which there are, you know, hundreds of fibers which are laid. You can see with a pitch of around 8 millimeters, with 4 fibers off and so on. 2 fibers from each of those groove are brought to a photomultiplier, I mean, like what we call a cookie, and then photomultipliers are attached here. And what is most important is, okay, you build them. Now, how well you test them before they are taken to Fermilab and installed. So we built a very fancy, I call that very fancy, because those days, once again, to build something of this type, we feel very proud about it. These are kind of detectors that you have 2 decks, so you can put 2 of them. And then you have regular cosmic ray telescopes, which are also made of scintillators, make a 3-fold coincidence, if you like. And then important thing is that you have 5 of such telescopes covering 5 corners, 1 at the middle and 4 at the corners and so on. And then run the system for overnight to be able to collect enough data for what is required. And again, the same thing it comes to. I mean, there are so many photomultiplier tubes. How do you even distribute power to them? How do you distribute voltage to them? Now, again, fancy devices are available. You can buy from Kayan. They will say 3,600 euros each piece. All that you require is take an input and put a bank of Zener diodes, which are the most accurate source of dropping of the voltage. You can have 30 volts, you can have 11 volts, you can have whatever you like, and put nice connectors from each one of them. You don't even have to measure them. Okay, they work so beautifully. And once you make it, becomes a useful thing to remain with you forever for putting that kind of thing. Then you go ahead and build probably the first CAMAC module in the department. Okay, so all that require is picking up these signals and then able to kind of control which telescope is giving you what trigger, and then you can bin them accordingly. You can find efficiencies, you can find uniformity of the detector, you can get charge distributions, you can get timing distributions, and then, you know, you qualify the detector the way you like. Of course, see, this is the fact. The fact is that it's not that everything you do by yourself. You don't go to workshop and say, please make a crate for it, or please make a mount for it. You actually draw the entire dimensions, and then you know exactly where each LED and each screw is fitting there. There is no surprises, okay? Because it is not that you depend on somebody, then the dimensions do not work and so on. Okay, you sit down and actually develop online software by yourself. Okay. Imagine writing codes when you had CGA monitors, right? You only have 80 by 25 characters, not graphics, right? And you can still display a histogram live as the cosmics come in. Okay, you have a, let us say, a code by which you can write online e-log. You can do everything you like. Only, I mean, this program even has screensaver when you go in the night, cosmic ray, I mean, because it takes time, right? You don't want to put on the thing. So you can even build screensavers on with characters and so on. So all I'm saying is that it looks probably simple to some of you these days where you have fancy tools, but when you want to build your own, when you want to discover your own, that is a real pleasure. Okay, and this code ran for decades, I would say, and then we are very happy to go and install these beautiful detectors in the D0 detector. You can see we liked very much because the D0 detector, when somebody looks at, all they see is only muon scintillation detectors which were built by TFR, because everything is padded outside by muon scintillation detectors, because they are used as veto detector to look for the muons coming from atmosphere rather than produced inside the collisions. So it's a very nice experience, but we didn't stop there. We went and actually contributed very significantly to the electronics as well. One of the biggest contribution is that D0 that time were looking for upgrade of for the D0 upgrade, they were looking for a new preamplifier. Some of the best preamplifiers in my experience I have seen were designed by physicists, not by engineers. The reason that I somehow think is I think they understand the best of how the detectors work. So therefore, the preamplifiers which are sitting on the detectors, they understand the characteristics, they understand the capacitance the detector is going to offer. They kind of understand the characteristics. So here also it was a great learning experience for us to go and build an upgrade preamplifier with them. Particularly, we worked on looking at very special front ends, which are, usually the front ends are made of very fancy FETs. And there are companies which make FETs specifically for very high GMs, right? Conductance. So therefore, we actually ended up upgrading the front end amplifier, of course, tested them, and it was one of the biggest contribution from us. We also went ahead and then actually built a system, what is called muon fan-out card test code, which was used not just by our muon scintillation group, but also the whole of D0 group as it is. And, one of the thing is the D0 muon system uses almost about 6,000 photomultiplier tubes, the special green extended photomultiplier tubes. How do you ensure that the gain of these all 6,000 counters remain, stable during the entire operation? So able to kind of monitor the gain of the PMTs was a big task. It was not easy, and you need to kind of collect the data, so-called in situ data. It's not that you switch off the whole experiment and say, now I'm doing calibration, so there is no run, right? You actually look for cosmics that are going on, and at the same time use that data to be able to kind of calibrate the PMTs, right? So using, so that is the calibration data. Then each one of these channels also has set of LEDs to flash them, and you use that as an absolute light to calibrate between these two. So this was again another major contribution of TIFR. Using this, we were able to kind of maintain the gain or determine the gain to better than about 10% of these values. I move on quickly to CMS. Of course, before we started getting on to actually building the so-called outer hadron calorimeter, we did a lot of studies in terms of the so-called Sushlik detectors, which was meant for E-cal at the time. So, for example, typically the scintillator with absorption plates here, with the fibers passing through and read by a photomultiplier tube, characterize them for various configurations, how the light yield is going to kind of happen. Obviously, it depends on what is the cross section of the scintillator plates. So in other words, what is the area per unit area, if you like, the coverage of fibers and so on and so forth. We also went ahead and did what is called a sigma tile. Sigma tile is a tile in which there is a groove that is made of a sigma shape, and you embed the fiber inside with the other end being, having a light reflecting place, and bring the light to, let us say, a photomultiplier tube. And obviously, before we build and optimize this, the tile, you need to also optimize and see what is the number of fibers, what should be the dimensions of these grooves, and so on and so forth. In some way, there is a parameter called, let us say, the length of the fiber that you embed in the detector versus the area of the tile. In some way, like L by A, you can say. That is what decides what is the light yield that you have. But obviously, the cost considerations also come into the picture, so you need to kind of look at that. All these studies were made before we started finalizing a particular geometry like this, what you see here. The close-up of this, you will find each one such a long detector has the individual tiles. You can see the sigma grooves inside embedded, and the fibers are brought into with a what you call a pigtail. So the wavelength shifting fibers are embedded in the scintillator, which gets spliced when it comes out of the scintillator, and then transported by using ordinary clear fiber, and bring all of them to an like an electrical conductor here, optical conductor, of course, connector, but it looked like a flat cable, flat ribbon cable, and then you connect that to another cable to take the light away, where you have a photo detector outside your magnet field, right? Now, one of the important factors is to kind of study these assemblies, study the fibers, study the splicing that I mentioned between them. So there was a fiber pigtail scanner that was made using photodiodes, and of course, this is a cassette of photodiodes into which the fibers are terminated with, and you have a stepper motor which will move the let us say UV source across the fibers, and then able to read, and you will be able to get, you can study the attenuation length of fibers, you can get the loss across the splice, you can do lots of things by building such kind of instrumentation. Again, this is a CAMAC based system. So this is what I said, that so there are these clear fibers, there are WLS fibers, they are brought to a connector, and then this is what the light that you read, and then you do a whole lot of data collection and to set up an acceptance criteria for, because you need to make thousands of them, because you need to make 450 odd detectors, right? So you need a lot of those pigtails. You need to have a very, very systematic study and then say which are accepted, which are not accepted, and so on. And that is how you can see that several thousand fiber composites that were actually made here and tested by the department. Another test that is required after you fully populate the detector tray, after you insert fibers and so on, is to study the entire detector with a radioactive source. Okay, this is what we call an XY scanner, XY movement, in which a cesium-137 source is moved around with about a millimeter position resolution, right? So you build such kind of a setup where the source is sitting here inside a lead container, brass container, and then you have XY motion to move forward. This is a little bit close up here, and the data that is coming from that connector is actually brought here and then read out online, and then it can make a histogram for you. It can also give you a surface profile of the entire tray. These are all these troughs and troughs you will see, because each detector is made of 6 tiles, and each one of them, as they cross the fiber boundaries, there will be ups and downs, right? Of course, you also use another type of wire source scanner, where this is not built by us. So this is built by Purdue University, but so the radioactive source is actually at the tip of a piano wire, which, like a gramophone kind of recorder, gets curled up inside, and then when it brought it out, it will go across the detector, and then then you see the light as a position of the source, and then you can cross calibrate. Oh, okay. Incidentally, this is the first colloquium that I gave as asset coordinator, so the date tells you here. Okay. Now coming to the last part of my, I hope I'll finish in not 5 minutes, but 10 minutes. This is the project for which more than half of my career I spent in TIFR. This is the INO project which should have come up at this place called West Bodhi Hills in Pottipuram. We plan to kind of build a tunnel below that mountain that you saw, and there will be a network of caverns. The biggest of that, more than 130 meters long by 30 meters by 20 meters, is where we planned to build about almost 50 kiloton detector, what we call iron calorimeter, magnetized iron calorimeter or ICAL detector. But there are also other tunnels, caverns where other experiments are supposed to come, like neutrino-less double beta, dark matter, even some of the material science experiments and so on. Some of these parameters you can see here connected with this particular, one of the most ambitious underground laboratory that we thought about it. Yes, this is the main purpose of INO was actually to measure atmospheric neutrinos and antineutrinos separately. I'll see a minute why that is a USP, and mainly look for the problem of ordering of tiny neutrino masses. That is what is called a mass hierarchy. There are also other ambitious goals that we had. All these were actually presented in this paper, white paper. So as I said, this detector is very big. It's of the order of a 5-storied building, about 150 layers of iron plates stacked here, each one of them weighing about 4 tons. And then the space that you have in between is into where you insert planar detectors called resistive plate chambers. And the trolleys that you see on either side are the one that will help you install or commission or repair any detectors that you have. What is USP of this is what is written as magnetic coils. The purple colored stuff is it's conventional electromagnet. The coils run through the entire the detector, and when you magnetize to a field of around 1.5 Tesla, this is where you will be able to, using which, identify the charge of the muon, namely mu plus, mu minus. There was a plan to build a so-called engineering module, which is a small set of this big detector, so that the engineering of it will be sort of understood. So I tabulated here the entire numbers here, but I'm not going to go through that. I'm only going to say that about 100,000 square meters of RPC detector area was to be covered in this detector, and we were supposed to instrument about 4 million detector channels. And I mean, just to give a perspective here, if you look at the kind of project that we were envisaging at that time, this is ICAL, what is needed, and all these were what I tabulated here are those which are the RPC detectors ever used in the world. Okay, and you can really look at the area that they have and compare the kind of ambitious plan that we had to build. The RPC detector, which was built first time here in TIFR, it's very simple to build. It has 2 glass plates which are kind of made to stick together parallelly with a gap to flow a special mixture of gas here. And the outside of these 2 glasses is where a semi-resistive paint is applied, so that you can apply a field across. And then the ones that you see across, what is written readout strips, are the ones which are orthogonal to each other to read data, read the signals from them. The best part of this is the bias of what you applied and the signal that is picked up are independent electrically. So it's a intrinsically very, very good detector. And secondly, with one gas volume that you have in the middle, you get cross-wire components, both XY coordinates. You don't put 2 detectors, one on top of other, to get XY coordinates. So intrinsically, it is a very beautiful detector. Yeah, I think I should move a bit fast. Yeah, I mean, again, the success story as far as TFR is concerned, our group is concerned, is we started this R&D program sometime in 2001 September, and a few years later, you can see that we have set up a large number of labs throughout the country here. Many of the students who passed out from the INO program went there and joined as faculties, and they set up RPC labs throughout the country. Okay, we also set up these kind of test systems where to validate. In fact, this setup, if you see, it has been running non-stop 24 hours for almost 15, 20 years, and it runs very well, and it doesn't create any issues tracking cosmic rays. It really tells you that this detector is very rugged when you want to use it for experiments like neutrino search. Neutrino experiments require long experimentation, 20 years, 20, 25 years, once you push inside a lab cavern. Okay, so these are really, really suitable, and the electronics that was used for such kind of test stands was all built. You can really see there was nothing that you buy and plug in, everything you design by yourself and put that. And when you want to design such an electronics for such an ambitious experiment, you really require a top-down approach. You really have to see, you are sitting in year 2000 and 2008, looking at an experiment which is going to run for 30, 40, 50 years. So what kind of architecture you require to build that? So this is the kind of brainstorming session, obviously D406, blackboard screen, that is. And then you pick up and you say that what you are looking at is cosmic ray particles passing through such detector, and then, of course, it's magnetized, so the tracks will be bent. I need to kind of look at the front end. I need to look at the digital front end, where typically I use field programmable chips, PLDs, to be able to implement all that logic under one. Look at hierarchical trigger system, look at hierarchical communication system where the data really comes back. So all these various elements that you see, all these various subgroup components that you require need to be kind of worked out very carefully. There were generations of chips that were designed inside the TFR, inside the INO collaboration, starting from all the way from hybrid microchips, which are built at BEL, then a large number of ASICs for the front end, timing detectors, again designed for so-called TDCs and so on. So all this was required, and we really need to build boards which are very, very tiny. Sometimes it's only about an inch long, inch height, but about 200 millimeters wide. Many chips were built by BRC and TFR collaborations here, and they were tested and working well. I just want to take a digression for 1 minute to show that, long ago, late 90s, when the Grapes experiment was requiring a TDC solution, where you require large number of channels, depend on commercial thing, it will be very hard. And so we went up and actually building a chip. That time it was a predecessor called TDC32. We actually sat down and designed a CAMAC module which can work very well for them, right? This was about 32 channel TDC, half a nanosecond resolution, and so that was a good solution for Grapes at that time. But why I was showing that today is that sometime later, a better version of that, what is called HPTDC, has become available by the same designer, and HPTDC was the choice for TDC for the neutrino experiment, which has come up, maybe 10 years later. So, I mean, this cross kind of, if I can say, collaboration in some way among our groups in terms of, high energy and nuclear, or, astro and so on, I think it helps a lot, not just among engineers, but also able to find solutions quickly and efficiently and so on. This I always consider to be one of the best example, where you do something for someone, some other experiment, and you find the same device will become really useful, cutting R&D cost, time for you when you want to set up things like that. So I still remember this used to be a pastime job after dinner to morning. And this is how all this scribbling, and when you really see the module coming up and working at UT for things, it's a great satisfaction, and it really helps. Of course, the UT engineers have really taken up the first module, and then built using HPTDC. Of course, FPGAs came on horizon by that time, and then they built beautiful systems after that. Why I said is, even for the TDC, even though the chip we purchased from microelectronics group from CERN, but later on, INO actually built not 1, 2, or 3 types of very, very high performance TDCs within the collaborations, right? From BRC, from IIT Madras, and so on. Now there are colleagues who want to kind of use these chips for not high energy physics applications, maybe biophysics applications, maybe some other applications. So this is how things happen. When you talk about in this hall, maybe there are users who will think, oh, the same device can be very useful. Now you are talking about these devices which are going to give you resolutions of the order of 125 picosecond. Okay, and not one, you will have 64 channels if you like. These are chips available, versions from FPGA, versions as ASICs. You ask for it, they're all available here, right? And they're built by our engineers, so therefore you don't have to worry about how to build. Sorry?
Chip fabrication.
Chip fabrication, of course, has to go somewhere, typically European foundries. But the entire design, I mean, everything is done here, right? Yeah, you only send the. So, for the want of time, I'm just moving forward. I would have liked to. So, when you put all these chips together, when you put all these designs together, you end up actually building very compact, very high density such modules. You look funny, it's a triangular board here. Okay, that is because you want to save space for on the detector. You want to have maximum space for as a detector, not for covered by electronics, which is a dead space, right? So this little module is going to take everything of 128 channels, the front end, and each one of them has an Ethernet port on it. So at the end of the day, what you have in the underground cavern is 30,000 such detectors, 30,000 such boards. Each one has an IP of its own. You sit anywhere in the world, you will be able to kind of access the way you access a computer in TIFR. Okay, so that is how you look for. I mean, gone are those days where you pay billions of dollars for Cayenne or LaCroix or something. I mean, these are all built by yourself the way you like them. Okay, so yeah, sorry, I'll I think move a bit faster. There are many such systems. This is a calibration system. When you have such a big data acquisition system spread over the entire lab, how do you ensure that each one of these signal that is coming up is properly sort of timed? Because as they travel through disparate lengths of cables, they end up giving you different delays. But at the end of the day, when you talk of trigger, they have to be at the edge, right? So you need to kind of have a system that calibrates very accurately in situ as the experiment is going on, adjust the time delays between them, not just only installation time, but even, if a variation happens due to other conditions and so on. So we had such kind of calibration systems. You have IEEE standard for such calibration system. You have like CERN bringing up what I call white rabbit for such kind of system. But this is our own white rabbit, maybe green rabbit, whatever. But those systems are all built here locally in this particular campus. And as I mentioned to you, the lookup table based technique, which we sort of invented for KGF, comes back as a system that is also can be useful to neutrino experiment here. So you divide the entire detector into segments and get the triggers sort of combined and bring to a level where you are able to generate trigger on fly. The data that is coming from 30,000 RPCs, they come like how they come into a big data center, like in a computer center through Ethernet switches here, and then also get the trigger from here, and you stitch the data together into an event based on the timestamps that you have, and then if the event is combined, if the event is constructed well, put that data into disk, but also ensure that you run all these data quality monitors that are run through. We don't even leave a power supply. We don't even buy power supplies from the market. We actually build high voltage power supplies that is going to bias the RPC detector right on the, using a DC-DC high HV converter. Okay, these are built locally with a very tiny space. You only have about a couple of inches by a couple of inches, right? So you should be able to have them. It should not generate any RF to the adjoining detector. It should not, of course, consume too much power, volume, heat, or whatever it is. These are devices which are built locally. And again, you see this funny shape of triangular shape because it should come at one corner of your detector. So again, here there is a huge number of such electronics boards that were built and installed and commissioned. Okay, when you operate such detectors, you also need to worry about the other ancillary systems. Just one example I wanted to show is the so-called closed loop gas system. The gas mixture is what is used for RPC detectors operation. So who will give you such gas systems? No one. No one will build gas systems for you. You need to design taking individual gases from the bottles, mix them in the proportion that you want, flow through the detectors, And don't waste the gas. It is not like LPG gas where you burn the gas, right? It's only used as a detection media. So you get that gas back. Obviously, little contamination will be there. You kind of purify the gas and push that thing back into. So that's called closed loop gas system. We design such systems and take help of an industry to build them here and so on. So when you want to build, such all this putting together, and when you build detectors, when you build electronics, when you put gas system, when you write software, everything, the proof of the pudding is to say that here is a little tiny toy of maybe 1:600 scale, but of the iCal detector, we want to put together and see that it indeed tracks the cosmic ray particles with a magnet on. So that really gives you a great satisfaction that all your efforts for decades come to an end, and say that yes, this is the detector now suitable for that can be kind of scaled up for massive neutrino experiment. Okay. Actually, I have something else, but I'm going to stop at this point of time for lack of time. So thank you very much for your attention, and I'll be happy to take any questions.
Any questions to sir?
The RPCs that were made,
Yeah.
tested long ago, even next to a recreation center, there
Yes.
is a small hut.
Yeah. Yeah.
Now, where are all these, and what's the largest size that is now ready but could not be used because of?
The iCal baseline designed size is notionally a 2 meter by 2 meter. It's actually about 1.8 by 1.8 closest. Such things we needed around 28,800 for the iCal detector that we planned so it's 3 modules, each module 150 layers, and 64 in one layer, and so on and so forth. It's a massive kind of detector effort. So we obviously started with a small detector and went 1 foot by 1 foot, 1 meter by 1 meter, and then 2 meter by 2 meter. We built a large number of them here, then went to Walchand Industries to see what we are doing, and then scale up for industrial production. They are supposed to give you a recipe that we can give it as a document for when you order them with glass industry. Typically, glass industries is where you put this. So then we went to glass industries like Saint-Gobain, Asahi, and so on. We took a lot of time. For example, there were many challenges. I told you sometime that you apply a semi-resistive coat on the glass on which you apply the bias, right? And it was found to be non-trivial. It's not like any paint, you just do it and it gives you resistance that you want. So we then teamed up with Nerolac paints and then developed this paint for a long time, lot of trials and so on. And then we at least made these 2 industries work for us, and we were quite confident that they can make them. We gave Saint-Gobain is made about 300 glasses, 300 gaps, and Asahi made about 50 of them in batches. No, maybe 60 of them in batches. But
These are all where?
they're all in Madurai, but we were asked to close down Madurai. Yes. Oh, sorry. I think Prajalakya has a question.
Hello. So in the KGF days, you said that the most data acquisition was digital, but you also had some analog signals taking. So can you just give details about how you collect the analog signals? Because I don't think there was these ADCs and something back then.
That's right. That's right. You asked the right question. Actually, it was a later thought. We didn't think about analog system in the beginning. So our system was predominantly so-called log pulse. That's why it's called log, because if you have a kind of exponential pulse and put a threshold at some voltage, you actually see the width is sort of logarithmically proportional to the height with a time constant which is fixed as tau. But the problem is with the lower pulse heights, you don't have a big problem getting a correlation between pulse height and pulse width. But if you are looking at very, very big events where the number of particles may be few tens or maybe 100, then the energy measurement will become very inaccurate, 20%, 30%. So therefore, we thought that why not, since the occupancy levels are low, so once in 8 of these channels, we will multiplex and get the analog pulse out. Okay. And then we have our complete system, which is basically peak holder, sample hold, ADC, and but the same microcontroller also runs the data acquisition system and puts things along. And when the no events, you keep on monitoring both analog pulse as well as digital pulse, and you do what is called log linearity of all the counters and keep that ready like a calibration. So it is a very beautiful system at the end. It worked very well. Yes. Yeah.
First of all, congratulations for the excellent talk and your
Oh,
contribution.
this is all work of hundreds
Yeah,
hundreds
but
or thousands
yeah,
of people.
yeah, that
Yeah.
I know, but your
Yeah.
your contribution to
Yeah.
development of so many instruments, and also thanks to your involvement in the TDC 32 design
Oh, it was a
development.
great
CRL which
experience.
you mentioned.
Yes, yes,
Of course, the later version which you mentioned SPTDC.
yes, yes,
In 2012, we replaced all commercial TDCs
yes.
with SPTDC,
SPTD.
and they are working,
Beautiful.
fantastic, beautifully for the last,
Yes, yes.
12 years. We do not calibrate. Initially, we started calibrating, but afterwards, we do
Actually,
not
there's no
calibrate
need. I mean,
because there is
simple
no
to-
need. Whatever the calibration value you get
Yeah.
is just theoretical value.
Yes.
Okay. And just in that context, since you developed, some of the group, in contest INO,
Hmm.
you developed this TDC,
Hmm.
which is very similar to HPTDC.
Hmm, hmm.
Just using the similar concept of HPTDC,
No,
yeah.
Yeah, technically, each device is slightly different. See, there are many classical algorithms that are available. Not today, they're very classical, they're very old. Now they become very useful because you are able to implement them by FPGAs. Okay, these algorithms are not new. But let me give you just hand-waving kind of a scheme how HPTDC works. HPTDC, you have basically CMOS gates, you put them, string them about maybe 32 of them, and push a clock there and see that at the end of the last clock, when it comes, obviously there will be delay, and put that delay with reference to the input clock. Now, CMOS gates are notorious for the dependence on power supplies, temperatures, and so on. So what you do is you pull all these power supplies to a charge pump in such a way that the error that you calculate, you make it zero. Until that time, you throttle the power supply so that that the exact delay is vernierinized, which means if I set a 1 meg clock, I want to see that it is exactly divided by 32. Of course, it won't be exact. It will either go up or go down, but you kind of adjust the charge pump. In a couple of cycles, it becomes standard. Okay, so now you use output of each of the CMOS gates as a vernier bits. So you say that, okay, if a 32, then 2 per like 5 bits I need for this. Whereas the coarse clock you use for the coarse counter. So maybe let us say 16 bits of coarse counter, 5 bits of vernier count, you get 21 bits, such a wide scale of a time measurement. You get about 25 nanoseconds, 25 picoseconds resolution clocks if you really combine 4 channels each. And that is how, the Alice time of flight detector was actually powered by HPTDC and Nino amplifier, and all the success of what they produced precisely belong to these two chips, which are both developed at CERN. The other technique is to run 2 clocks, one slow clock and one fast clock, and see where they actually meet and after how many cycles. So the second one will become as a vernier for the first one. The third method is where you run a clock through flip-flops, and then the output of which is taken as the vernier out. And now you count how many flip-flops that you have in the middle before, again, similar to CMOS gates. So either you have a flip-flop thing, you have the slow clock, fast clock thing, or you have CMOS gate delays. It's something like in some way is using delay of an element as a timing thing. You can take a nice RG174, it will be a beautiful lump of clock, okay, like ordinary cables also. But if you want to do something of programming later on, calibration, etc., that is what you do at the back end. So the FPGA part is using the slow clock, fast
just
clock.
quickly to understand, this HPTDC, of course, we got the ASICs
Yes.
from Sharn,
Yes.
that time plus
Yes.
Anwar also.
Tonwar,
So this ASIC right now,
Yeah.
you develop
the
here
BSc,
only,
the BSc group developed.
in
Yes.
the BSc group, and then you manufacture somewhere.
Correct,
Okay.
correct. Actually, they have right now two versions. One is on FPGA version, and the other one is on the ASIC version. The FPGA version advantage is that you can also run the post processing right on the FPGA itself. You don't need another FPGA sitting with an ASIC like HPTDC. When you use HPTDC, you also require an FPGA. Okay, but here it is one device that 128 channels he was able to kind of run there in one FPGA. So
Thank you.
yeah. IIT Madras. Yeah, I mentioned during the thing, but yeah, I didn't talk to you more details about IIT Madras. Yes, yes. And you're talking about typically 125 picoseconds resolution. Yeah,
Yeah.
sorry.
So you mentioned about this preamplifier for the D0 experiments.
Yes.
So that was for which type of detector? I missed that point.
These are calorimeter, so liquid argon detectors for that. And that was initially meant for it. There was already existing a preamp with about 5 pf gain, I think, at that time. But the problem is the bunch crossing has moved from roughly, I think, 3.5 microseconds to about 130 nanoseconds or something like that. So we needed to design a new preamp. Also, the power, the previous amplifier was picking up too much power and so on. So there were a set of such issues. So we wanted to kind of change, mainly we wanted to change the input side because, basically the noise factor is something like a √2 dependence on the number of FETs in the front. So those days they were using from Toshiba, the front ends. As I told you, the FETs are very specialized, especially if you want to have a bigger FETs, the noise margin becomes proportional to that device. So therefore, what they said is that maybe we should use, though they're a bit expensive, but use something what are made interfet or something, a company I don't remember. So I kind of got engaged with that, and of course, in the process, we also changed the gain of the preamplifier. Now that is what is used till end of D0.
So one question is, see, you have been talking about the front-end electronics, data acquisition and other things. What is the most craziest idea you have seen in last, say, a decade?
I think
which, you think that has a good possibility for future?
Unfortunately, I stopped at a time where I couldn't show you one such example. That is what we have been working just before we closed the neutrino experiment, and you are well aware of it. So, namely, just like HPTDC, the other, I think, major invention that I changed the shape of data acquisition systems is digitizers. So all you see throughout the presentation is something you measure one parameter at a time. You use a component to measure pulse height, you measure timing, you measure charge, you measure this, that, etc. The idea is that in olden days, you couldn't have done digitizing each pulse. Someone was asking about how do you manage the rate of the detectors is high? We couldn't do it because number one is digitizing at that speed is one thing. Secondly, the data that is collected, how do you take it to the back end? So that you don't have to build so-called triggered systems, you can build triggerless system. Pick up all the data, push it on backend, and then happily run the algorithms later to be able to throw unwanted data. That couldn't be done because of communication as well as the digitizer. Now with the DRS kind of digitizers, where around 200 picoseconds is a good bin where you can digitize that data. And also you can do a lot of processing at the spot because you team up with a DRS followed by an FPGA right there. You can run all the algorithms locally. So therefore, now it has become not just picking up data, acquire one data at a time. You pick up the entire pulse profile and then do filtering. You do whatever best filter that suits to you for your spectroscopy applications, timing applications, pulse height applications, whatever you like. I think that has changed in a big way, and it is becoming very affordable these days because typically each chip has 8 to 9 channels, and then one can easily kind of do any data acquisition system that you can look at.
Are there any emerging technology which are coming in the engineering from, say, communication sector or from other sectors? I was asking.
Okay, so of course it is a little bit detector specific. For example, if you are talking about LHC in the previous let us say phases where you couldn't think of using very let us say close to vertex kind of detector, tracking detectors, for example, you could never think of using them for trigger, right? Because you have 40-50 million detector channels. There is no question that you will be able to kind of use that data only. You are only using it for let us say tracking, really speaking. And triggers are typically used by muon detectors or maybe calorimeters before that and so on. Now, what one is able to kind of do is bringing I mean, it's not so much about hardware per se, but hardware combined with putting up a lot of intelligence right in the front end, just still ensuring that you have a low power electronic sitting there, because you can't really have too much power drawing, or for that matter, even material budget is also not possible at the vertex. So one is able to kind of now bring track reconstructions using FPGAs and the algorithms that are running inside FPGAs right on the tracker. So, and that is what has opened up something totally new for high counting rate applications. It was never a challenge for non-accelerator kind of experiments. You have typically thousands of channels, but those electronics were kind of okay. Even if you're looking at pulse shape discriminations and those kind of things, DRS or other digitizers are available to you. So I think that is the main idea. So the architectures of DAQs have gone major upgrades, but the important factor is many of the individual components roles earlier you were doing using discrete electronics. Other than the real analog front end, the FPGAs and ASICs are taking over. Yes.
Mentioned about the EEPROMs being used as LUTs or programmable logic.
I'm sorry, it was not EEPROMs, it was EEPROMs
Okay.
at that time.
Okay, EEPROMs.
Yeah.
Yeah.
UV erasable program.
I was just wondering how can a EEPROM be used as LUT? I mean, I think at the end they were being used as some programmable logic, like something like FPGAs.
So see, you are born at a time when EEPROMs have gone out of the thing. It's same as you use as a static RAM. How do you use? I can put a table in a static RAM, and I use address of the RAM as the one to look up pigeonhole, right? And I already write what I need for the output of the trigger as the data bits, isn't it? So oh, you already know.
LUT is for implementing the.
Yeah, it's the same thing. Only thing is it is.
Resetting the FPGA, they are putting in the EEPROM.
And if I need to change, unfortunately, I have to pick up the EEPROM out of the socket, erase it, and put a new code. It's not like so happy like you run a code on GTAG and the whole system works. Of course, it's obviously very efficient, but yeah.
Okay, thank you.
Yeah.
Questions from Zoom room online? If anybody has a question on Zoom, you can just unmute yourself and ask.
Zoom don't. Yeah.
So I welcome everybody to please. Yeah, please go ahead. So that
Thank you.
in conclusion, I just want to add, I am very happy that Satya said I ran out of time. So it gives me excuse to invite him again to give his answer.
No.
Please join us in.
Thank you very much for sitting through. I mean, it has been almost half an hour past 5. Thanks. Let us go underground. By the way, there are thousands of such pages. I discovered that I wrote every drawing by hand and all the notes by hand. I mean, if you come to my room, I'll show thousands of such papers.
You donate them to archives.
No, those days you don't have circuit diagram, you don't draw on, it was all by hand. thanks to Japanese, they used to give these templates that to draw logic gates and so on. You will remember that. So no, each of this plate is hand drawn. There was, and each of the memory maps, pin connections, operating system. I had written about this thing